Physics is the study of matter, energy, and how they interact. It seeks to understand the fundamental principles governing the universe. From the smallest particles to the largest galaxies, physics explains how things move and why they behave the way they do. Why is physics important? It helps us understand the world around us and the laws that govern it. Innovations like electricity, computers, and even the internet stem from principles of physics. Without it, modern technology would not exist. Our journey in physics starts with classical mechanics, pioneered by figures like Isaac Newton. We then move to modern physics, where Einstein's theory of relativity reshaped our understanding of space and time. Finally, we delve into the mysterious world of quantum mechanics, which reveals the strange behavior of particles at the smallest scales. This essay will take you through these stages, making complex ideas simple and engaging. Ready to explore the universe? Classical physics lays the groundwork for our understanding of the physical world. It began with the observations and theories of ancient scientists and philosophers. However, it was Isaac Newton who truly revolutionized the field. His work in the 17th century provided a framework that explained motion, gravity, and the behavior of objects. Newton's ideas were groundbreaking. He formulated laws that described how objects move and interact. These laws apply to everything from falling apples to orbiting planets. Classical physics focuses on the macroscopic world, the things we can see and touch. Before Newton, people had varying ideas about motion and forces. Aristotle, for instance, believed that heavier objects fall faster than lighter ones. It took Galileo's experiments to debunk this myth, showing that all objects fall at the same rate in the absence of air resistance. Classical physics is intuitive and aligns with our everyday experiences. It gives us the tools to predict how objects will behave under different conditions. This predictability is why classical physics remains a fundamental part of science education. Isaac Newton's three laws of motion are the cornerstone of classical mechanics. They describe how objects move and interact with forces. The first law, or law of inertia, states that an object remains at rest or in uniform motion unless acted upon by an external force. The second law quantifies force as mass times acceleration. The third law states for every action there's an equal and opposite reaction. Together, they describe how objects move and interact. Gravity is one of the most familiar, yet mysterious forces in nature. Newton's law states that every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance. This explains why apples fall and why planets orbit the sun. Newton's insight unified the heavens and the earth under the same physical laws. Gravity acts at a distance, affecting everything from particles to galaxies. It shapes stars, planets, tides, and the universe's structure. Einstein advanced our understanding of gravity beyond Newton's laws. Section 5. Transition to modern physics. The transition from classical to modern physics began in the early 20th century. Scientists realized that classical physics could not explain certain phenomena, such as the behavior of light and the stability of atoms. This led to the development of new theories that reshaped our understanding of the universe. One of the most significant figures in this transition was Albert Einstein. His theory of relativity revolutionized the way we think about space, time, and gravity. He proposed that space and time are interconnected, and that gravity is the result of the curvature of space-time caused by mass. Modern physics also includes the development of quantum mechanics, which describes the behavior of particles at the atomic and subatomic levels. This field of study revealed a world that is fundamentally different from our everyday experiences. Particles can exist in multiple states at once, and their behavior is inherently probabilistic. The transition to modern physics was not just a shift in theories but a complete transformation in our understanding of reality. It challenged long-held assumptions and opened up new possibilities for scientific exploration. Section 6. Einstein and the theory of relativity. Einstein's theory of relativity has two parts: Special and general relativity. Special relativity from 1905 introduced that the laws of physics are the same for all in uniform motion. It revealed the speed of light is constant and time and space are relative. E equals mc squared shows energy and mass are interchangeable. General relativity from 1915 extended these ideas to gravity. Gravity is a curvature of spacetime caused by mass. Einstein's theories impact everything from astrophysics to GPS technology. Section 7. SpaceTime Continuum. The SpaceTime Continuum is central to Einstein's theory of relativity. It combines 3 dimensions of space with the 4th dimension of time. This challenges our perceptions of space and time as separate. The curvature of spacetime is what we perceive as gravity. Massive objects create dents in spacetime, influencing motion. Earth orbits the Sun along a curved path in spacetime. Section 8. Quantum Mechanics. An overview. Quantum mechanics is the branch of physics that deals with the behavior of particles at the atomic and subatomic levels. It reveals a world that is fundamentally different from the macroscopic world described by classical physics. In the quantum realm, particles can exist in multiple states simultaneously, and their behavior is inherently probabilistic. One of the key concepts in quantum mechanics is wave-particle duality. Particles such as electrons exhibit both wave-like and particle-like properties. This duality is evident in experiments like the double-slit experiment, where particles create an interference pattern, a characteristic of waves. Another important concept is the uncertainty principle formulated by Werner Heisenberg. It states that certain pairs of properties, such as position and momentum, cannot be simultaneously measured with arbitrary precision. This principle challenges the idea of determinism in classical physics. Quantum mechanics has led to numerous technological advancements, including semiconductors, lasers, and quantum computing. It provides a deeper understanding of the fundamental nature of reality and continues to be a rich area of research and discovery. Section 9. Wave-particle duality. Wave-particle duality is one of the most intriguing and fundamental concepts in quantum mechanics. It proposes that particles such as electrons and photons exhibit both wave-like and particle-like properties. This duality is not something we observe in the macroscopic world and challenges our classical intuitions. The double-slit experiment is a famous demonstration of wave-particle duality. When particles like electrons pass through 2 closely spaced slits, they create an interference pattern on a screen behind the slits. This pattern is characteristic of waves, suggesting that particles travel as waves. However, when the particles are observed or measured at the slits, they behave like particles, passing through one slit or the other. This experiment shows that the act of measurement affects the behavior of particles, a phenomenon known as the observer effect. Wave-particle duality has profound implications for our understanding of nature. It suggests that particles do not have definite positions or paths until they are measured. This concept is central to many quantum phenomena and highlights the strange and counterintuitive nature of the quantum world. Section 10. Quantum entanglement and superposition. Quantum entanglement is a phenomenon where particles become interconnected, such that the state of one particle instantly affects the state of another, no matter how far apart they are. This spooky action at a distance, as Einstein called it, challenges our classical understanding of locality and causality. Entangled particles share a combined state, and measuring one particle immediately determines the state of the other. This phenomenon has been experimentally verified and is a key resource for quantum technologies like quantum computing and quantum cryptography. Superposition is another fundamental concept in quantum mechanics. It states that particles can exist in multiple states simultaneously. For example, an electron can be in a state where it is both spin up and spin down at the same time. This superposition only collapses into a definite state when measured. These concepts are not just theoretical curiosities, they have practical implications. Quantum entanglement and superposition are the basis for developing new technologies that could revolutionize computing, communication, and encryption. They represent the cutting edge of our understanding of the quantum world. Section 11. Conclusion. The journey from classical to quantum physics is a fascinating exploration. Classical physics laid the foundation for our understanding of the physical world. Modern physics, led by Einstein, expanded our understanding of space and time. Quantum mechanics revealed a world where particles behave in strange ways. Understanding quantum mechanics is crucial for advancing technology. The journey of physics continues to inspire and intrigue.